Hello, I'm Aki Vehtari. I'm an associate professor at Aalto University, and I'm also part of Finnish Center for Artificial Intelligence, and I'm part of Stan and Arvi's development teams. And I'll talk now about some of my favorite inference diagnostics. Outline for the talk is a bit of general guide for running inference many times, and then convergence and accuracy diagnostics for MCMC, variational inference, importance sampling, and as a bonus, just a little bit about stacking for non-mixing Bayesian computations. First, running any inference algorithm, it's a useful idea to check that you get similar results with different initial values, different random seeds. And then it's just a problem that how we define similarity. Here we have started different MCMC chains from different places. If this would be optimization, we would have just some threshold to decide when they are similar. But when they are MCMC going around, we need something more probabilistic. I assume that you know already what is Markov chain Monte Carlo, but just reminding a couple terms and important properties. One is that asymptotically chain spends, for example, 90% of time where 90% of posterior mass is. So this is useful property because then that's how we learn where different amounts of posterior mass is. And in infinite time, this would be also true no matter where we start. If we would run enough, this would be also representative, and we would still spend 90% of time here. But when we run this only finite time, then it's useful that we can remove these non-presentative initial points. And so this is often then called warmup, although then many modern MCMC algorithms, like in Stan and PyMC tree, are also doing during the warm-up some additional adaptations. But one part is that we want to remove these non-representative parts because of choosing some initial values. Then another part is that if that finite time is too short, it's possible that this Markov chain is not exploring yet the whole interesting region like this part, and where the blue line is now describing where the 90% of mass is. Also, when using MCMC, it's useful to run several chains. It makes the convergence diagnostic easier, and it's also more safe, especially in multimodal cases. So we can start chains from different starting points. In this case, I've used intentionally Markov chain algorithm that is quite slow, making small steps, so we can exaggerate these convergence issues. And it's easy to see that in the beginning they don't look so similar, but eventually they go in this 90% region. The same chains illustrated now as trace plots. And now we would say that these are not yet converged. For example, looking at this chain, we can see that there's a bit of downward trend for θ1, but also the overall variability of this chain is much smaller than variability of all the chains. And this is something useful for look in convergence. And then if we run longer, now the same chain is the top chain here, and now we can see that it is exploring much better, and it seems that these different chains have similar variability, and we might assume that maybe this is converged. These kind of fuzzy warm plots are quite common, but there are cases where they are not that useful. Here are trace plots from an example where you can see that it's not that easy to say whether this is converge or not converge. You can make your own guess, and I'll come back to this example later. So other thing is, of course, also that then looking at these kind of trace plots, we have a lot of parameters. There's a lot of work to look at them, and it's better to get something more quantified value, which would tell us, and it would be more easy to check than these values. So I'll talk about R hat for MCMC Converge diagnostics, which is based on the idea that after warm-up, chains should eventually produce the same mean and variance estimates, and then they should be stationary. And then R hat does this by comparing within chain and total variance estimates. And I also later mentioned split R hat, which compares also then beginning and end of the chains after the warm-up. Using the same example, reminding just that how it looked like if we look at these trace plots in the beginning, not yet converged, and for example, this one giving higher values still than the others, and not yet kind of exploring all the this interesting region, and then how it then looks later, and then how this same looks from the point of view of R hat and these within chain and total variance estimates. So that chain I highlighted before is illustrated here now with the Gaussian distribution. So I've computed for that chain, so 50 warm-up, 50 post-warm-up iterations. Based on 50 post-warm-up iterations, I've computed mean of that chain, those draws, and variance of that chain, and illustrated with Gaussian normal distribution approximation. The same way I've computed then for each chain these means and variances, and we can see that these chains are not yet producing similar estimates. How we can then quantify this process is that we compute within chain variance estimate. So we compute these variances from each chain and make average of those. Average of those within chain variances is now 0.5. And I illustrate that variance then with this dashed line normal distribution. Then we can also compute total variance estimate, which combines the variation between chains and these within chain variances. And we can see that there's more total variation than any single chain has done. And now this total variation is 1.4. And now ratio of these two values and then square root of that gives us R hat, which is now 1.64, indicating that we have not yet converged. There's not yet, these chains are not yet mixing well. So this was after 50 warm-up, 50 post-warm-up iterations. And then we can continue running more, 500 warm-up, 500 post-warm-up iterations. These start to be more similar. Within chain, variances are 0.9, but still the total variance from all the chains between chain variation and within chain combined is larger. And R hat is above 1 and indicating that we can still do better. 5,000 warm-up, 5,000 post-warm-up iterations, and now these are much more similar. And then when we compare within and total variance estimates, they're very close to each other. Take a ratio of that square root, and then this rounds already within 2 decimals to 1. And we say this is converged. And just reminding that in this case, I had intentionally chosen a case where this convergence speed, mixing speed is not that good, and that's why we needed quite many draws. Now we had in the beginning, the R hat was larger than 1, and then it went towards 1. And so the idea is that this total variance estimate var hat plus reminding us that it's overestimate. And then the within chain variance estimates tend to underestimate these variances. And then this ratio and also square root of that ratio should be larger than 1. But then we also know that these both estimates approach true variance when sample size goes to infinity, and then r hat goes to 1. So that way we know that this diagnostic eventually can tell us when we reached a good situation. There are different versions of r hat. The first one was published by Gelman and Rubin in 1992. And then sometimes this is also called then Gelman-Rubin statistics. But since there are later versions, it would be better to just call it r hat and then mention which version. Brooks and Gelman made a correction to the first version. Then in Bayesian data analysis 2, there's simplification because some of these kind of terms, computations in these earlier ones were not actually needed with the sample sizes usually we have. And then in Bayesian data analysis 3, there was an addition of split r hat. So in the usual r hat case, it's easy to see a difference between these two chains which have different marginals. But then there might be cases where the chains have actually the same marginal, but still have within trend. And then the split chain approach just splits these in two and then compare 4 different parts like this. Then this year, our paper published now online in Bayesian analysis is then the 5th version, which adds rank normalization to handle infinite variance and folding to improve detection of scale differences. And I talk about this version now more. So these earlier versions fail if mean or variance is infinite, because this r hat is based on comparing these within and total variance. But if the mean and variance are infinite, then of course this estimate doesn't make sense. We also noted that it's weak detecting scale differences. So if the locations are same, but there are differences in scale, it's also weak for, these versions are weak for that. So when will we have these kind of that mean and variance is infinite? The example is Cauchy. And we've been recommending at some point, for example, half Cauchy distributions as a prior, and then we might have these Cauchy-like tails, and then it might be that we have actually infinite mean and variance also in practice. And you can recognize the left-hand example here, what I showed also before. It's sampling from Cauchy, and now you can try to guess that are these both converging, one of them converging, or neither of them converging. And it's not easy to see it from this plot. And these earlier r hats would have also failed. So now if we have this infinite mean different location, so the previous r hats would just already report values really close to 1, while now this new version can detect that these locations are different, for example, locations of Cauchy. And then, of course, when we have same locations, same scales, both give values close to 1. But there was also that even with finite mean and finite variance, if they had the same location but different variances, again, these older r hats, so values close to 1, and then the new one can detect these differences. And if these all are same, then both give values close to 1. So how we do that? We used rank normalization, which helps now that it works with infinite variance and mean, and it's also make it more robust with finite but high variance. So we replace original parameter values with their corresponding rank normalized values, also known as expected normal scores. And this is not a new idea. It's been done already in 1930s and common, for example, in genetics. And so we replace each value first by its rank within the pooled draws from all chains. So pool all the draws, sort them in order, and then we get ranks. Now, then transform these ranks to normal scores using the inverse normal transformation. So here we have the ranks, and then we use these, change the ranks to fractional ranks with these, using these fractional offsets, and then inverse normal transformation, and then these jets are distributed, normally distributed. And then when they are normally distributed, they have finite mean, finite variance, and overall provide better efficiency for this kind of normal assumption-based test like R-hat is. Additional benefit is that now the rank normalized R-hat is invariant to monoclonal transformations. In these different PPL frameworks, we often use parameter transformations to improve the sampling speed, and then it might be a question that in which space we should look at the convergence. And now it's good that then we get the same diagnostic value for whether we analyze theta or log theta. Of course, there's a then later I come back to difference that when we are looking at the effective sample size and Monte Carlo standard errors, then it matters which one we look. But as a first step diagnostic, it's good, useful to have this invariance. In addition, we do something that we call folded ranks, but this is just ranks from absolute distance from median. So we now sort the draws according how far they are from the median, and then use those as ranks. And then since they are now measuring, these ranks measuring the distance from the median, this improves the detection of scale differences. And you see, can look at the more details in this our paper. So this rank normalized R-hat is robust as a first step diagnostic, but eventually, of course, we should look at this Monte Carlo error for all quantities of interest, how accurately we are estimating anything. But this Monte Carlo error for these quantities of interest, they need to be considered in the context of that quantity. What is the total variance of that quantity? What is the meaning of that quantity and purpose of that quantity? How accurately we need to know that quantity. And then when we have models with a lot of parameters, it would be a more intensive task to think about these for every parameter in the first place. And so these R-hats are useful to first diagnose something. But then eventually we want to go also for these Monte Carlo standard errors. For independent draws, we have that Monte Carlo standard error is variance of that parameter and then divided by sample size and square root. For Markov chain draws, because of the dependency, instead of having independent draws, we divide now with effective sample size. And so the effective sample size can be smaller or bigger depending on what kind of correlations we have in these Markov chains. And usually this is smaller, although like dynamic HMC can give us also sometimes bigger ESS than this. This effective sample size is also useful as a generic scale invariant efficiency estimate for quantities of interest, because we don't now need to remember what is or look what is the variance of each estimate. So it is kind of the relative to that. And then when we are looking efficiency for many parameters, this scale invariant measure is useful to look at the overall efficiency. And it's also that when you kind of use to think about different parameters or functions of them, you might be just from that ESS is high, know that, okay, it's very likely that then Monte Carlo standard error is also small enough that I don't even need to look it in more detail. So these effective sample sizes are based on estimating autocorrelation of Markov chains. But then in addition, when we are running multi-chain, then we use these within chain and total variance estimates also when we combine the autocorrelation estimates from different chains. And so it is kind of using R hat again, although now non-rank normalized version, because in this case, we really, there's a difference whether we are looking expectation for theta or expectation for some function of theta. And this effective sample size can be different for these two. Okay, since this effective sample size can be often different for these different functions, we can of course look it specifically for certain functions. But then we have also one generic idea that how we can look that if we don't know yet for which functions we do these computations. For example, we first just want to check how good the sampling was, but then we use the draws to derive further quantities. So we can look kind of that these different expectations of different functions would require that we have good efficiency mixing all over the parameter space. So we can look at the local efficiency and quantile efficiency. This first plot shows effective sample size for small intervals, how well we can estimate that how much posterior mass there is in some small interval. And now we can see in this case that we have quite good effective sample size for many small intervals, but here in tails, close to 0. So we are completely failing, and it's unlikely that we can get good estimates for all possible functions F. Alternatively, we can look at quantiles. So each dot is how effectively we can estimate some quantile. It seems that we can estimate median quite well, but many of these tail quantiles really bad. And in these cases, if we get kind of efficiency of 0 for tail quantiles, we should actually suspect also these others. But so clearly we see that now the sampling is specifically inefficient in tails. Here's for this then the example where we have good efficiency also in tails. So slightly less efficient in tails, but still 2000 is effective sample size in tails is already good, and the same for quantiles. This is typical shape for dynamic Hamiltonian Monte Carlo, that it has higher efficiency for quantiles and mean, so kind of the near the bulk, and then lower efficiency in tails, but in this case, very good efficiency also in tails. But since, again, so these plots are useful for seeing more, but we don't want to always look at those plots for every parameter. So we decided to give two summaries, which we are now printing, for example, by default in posterior packets. Bulk effective sample size, which is then effective sample size for rank normalized mean. And then using the rank normalization here, because then it's working also if we have infinite variance or infinite mean. And then describing kind of how well we can estimate different bulk quantities. And then tail-ESS, which is the minimum ESS for 5%, 95% quantiles. And so this is useful as quite often people are looking for example 90% intervals, and previously ESSs were only shown for mean, but it's quite common that these tail effective sample sizes, so for the quantiles, are actually much lower, and then that's why it's useful to see also those. And then of course there are functions that users can compute ESS for any quantity they want, but these were thought that these are two good summaries now to do. And then here's a plot also showing kind of it's possible to look also, are these ESSs improving if we get more draws? In this case, the bulk is improving, but the tail ESS stays constant, meaning that it doesn't even help if we keep sampling more and more. For this, in this specific case, now the MCMC is failing to give good estimates. Since we use this rank normalization, where we were then thinking what other things we could do with ranks. So rank normalized values have these normal distributions, or should have normal distributions in case of good mixing, but then just the ranks should have uniform distribution. So we replace values by the ranks within the pooled draws, and then given good mixing, ranks within each chain should be uniformly distributed. And now we can see that this chain number 2, it has more large value ranks, while chain 1 and chain 3 have less high ranks. So clearly not mixing. And then another case where then these look more uniform. So it looks at Converge and good mixing. And now you can recognize these trace plots I showed earlier, and then corresponding histogram. So these chains were mixing well, and these chains were not mixing well. And it's much easier to see it from these rank plots than from these trace plots. We know that some people then like these rank plots, but they have also a bit of a problem. So how do we know that certain histogram of ranks is uniform? One way to look at this is that even if we would be drawing from completely known uniform distribution, there would be just randomness that different bins get different number of draws, and this how many draws each bin get, it's binomially distributed. And then we can make this kind of envelope showing what would be the expected variability in bin counts. The one problem here is that this bin size is arbitrary. So for the same draws using different binning, we might get then that some of these bins just go by chance over. And actually, of course, with more bins, there's this kind of multiple comparison problem, so it's more likely that we go outside of these bins. And then we think that it would be better to use an approach that doesn't have this bin size selection, and using empirical cumulative density functions. So here's with the red line for the same data, how the ECDF looks. fractional rank and how the cumulative density increases, and there's some randomness. But then we can have also this envelope showing kind of if it would be from the uniform, what would be the natural variation around the perfect diagonal. And in this case, it seems to be staying there. One problem with this plot is that it's mostly white space, and kind of the dynamic here is quite small. So we can subtract the diagonal from this and look just ECDF difference. So it's the same red curve, just tilted now 45 degrees, removing the white space. And if this now stays inside the envelope, it's likely to be describing draws from a uniform distribution. Here's an example then where, again, this binomial envelope or histogram fails. There's a larger than expected mean. All bins stay inside, but if you look, you could see that on average, then bins here have smaller kind of counts than on average bins here. So this binomial distribution envelope is not taking into account this dependency here between the bins, but in ECDF, we can see it. So in this case, it was larger than expected mean, meaning that for small values, we are not cumulating the density as quickly. And then eventually we have more of those larger values, which make the average larger, and then we get density increasing, or the cumulative density increasing faster. And again, better dynamic range, looking at the ECDF difference. So there are less small value draws, we go down, and then there are more larger values and we go up. And we can do this also when comparing multiple chains. So you can see example, no convergence. Some of the chains have more small values, some of the chains have less small values, and then example where we have good mixing. R-hat is almost always used for univariate marginals. There's also multivariate version. One reason it's not possibly used that much is that because of kind of the often we don't have multivariate distributions, and maybe this rank normalization would improve that. But there seems to be also other issues in this comparing multivariate normals. The reason why, however, these kind of multivariate diagnostic would be interesting is that it is possible then that we have kind of good mixing, and it shows also in marginals, but it can be also a case where the marginals look just fine, but then we have a difference that one of the chains has more draws here and more draws here, and another chain has more draws here and more draws here. And so we need to have something which is joint approach. And then Ben Lambert came with this idea using flexible multi-class classification methods. So we can divide these posterior draws to training and test set. In training set, we use the values to predict that from which chain the draws come from. And then the classifier could learn that, okay, these values are likely to come from the gray chain. And it could learn then that these values are more likely to come from the black chain. And then if it also predicts these well in a test set, we can get a value which quantifies how much better than random chance we are predicting, which will give us indication of lack of mixing. Okay, so far I've talked about this MCMC convergence and accuracy diagnostics, R-hat version 5, rank normalized and folding, effective sample size estimates, Monte Carlo standard error, local bulk and tail ESS, rank ECDF and ECDF diff plots, and R star. Then about variational inference conference diagnostics. Black box variational inference, such as autodiff variational inference, ADVI, use Monte Carlo evaluation of gradient and elbow. And this Monte Carlo evaluation makes these gradient and elbow estimates stochastic. And then that's why stochastic optimization methods are used. Often, the stochastic optimizations are done so that using decreasing step size rules to fulfill Robbins-Monroe condition, so that in infinite time we would reach optimum, and then when the step size goes to 0, there's no stochasticity anymore. But in practice, we don't have infinite time, and we have only finite time, and in practice this optimization is stopped very early. And then that means there's a lot of stochasticity in these results when stopping early. Usually these stopping rules are looking at these change in elbow in some window, because again, there's stochasticity also estimating that elbow, and then looking when it decreases less than some threshold. It's also common that this, after the stochastic optimization is then stopped, using only the last iteration. But since there's a lot of stochasticity, there can be also a lot of stochasticity in which iteration we choose. Polyak and Rupert have proposed this averaging of the iterations long time ago, and it has been recently rediscovered, or for example, with the name stochastic weight averaging. And then this average of iterations converges much faster to the optimum, and it's also much more stable end result. Now, if the step size is fixed at some point, the stochastic optimizations ends up being a stationary stochastic process. And hey, I've just talked to you about more than half an hour about how to diagnose stationary stochastic processes. And we have a paper which was accepted to this year NeoRIPS. And we can use R-hat to detect approximate convergence and warmup length. Again, kind of what is the part we need to remove before we've reached the stationary part. And then Monte Carlo standard error to assess how close the average over iterations is to the optimum. We can also use this Pareto K diagnostic, so that we are assuming that this stochastic process has finite variance, and we can look at the values of from the stochastic process, the tail, and fit generalized Pareto distribution there, and look at the shape parameter K of that Pareto distribution to identify how thick the tail is and infer from there whether it has finite variance. Here's an example. So this is now showing negative elbow, so smaller is better. It's typical that in the beginning we get very quick progress, and then like Stan has a default elbow threshold like this, so it stops quite quickly. But we can see that if we would continue, the negative elbow would keep getting smaller, but there's also some stochasticities there. Now, if we look at instead, so the blue line shows the distance between now these our variational parameter estimate and the true values. And we can see that this was quite early moment to stop. If we continue longer, we get these variational parameters much more close to optimum, and we get decreasing. We can also see this huge randomness that here, if we stop at this point, we get much closer. And if we stop at this point, so if we choose just the last iteration, there can be huge difference how close to the optimum we are. So then, two things that can help. Average iterations. Here we are just averaging over some fixed window, and you can see already that it gives better estimates, but also less variation. So you are less lucky when you stop. In addition, we can look at this R hat. Okay, it seems that we've reached stationarity here, and then start averaging more and more iterations. And then we get even closer to the optimum and less variation there. So much more stable estimates, much more closer to the optimum. So the R hat, we usually recommend computing it from multiple runs, but since we have this split R hat comparing the beginning and later part, we can use also it's just for one run, and you can see here then how the R hat eventually comes down, and then there's different number of variational parameters, and it's common that we need to run more iterations in higher dimensions. Here's also kind of the illustration that how the dimensions of dimensionality of the variational parameter affects. So it's usually easy in very low dimensions. It's easy to make these toy examples where we get close to the optimum. But when the number of variational parameters increases, usually the performance gets much, much worse. And if we stop with the too early with the elbow rule, even the averaging iterations doesn't improve much. But now running longer using this Monte Carlo standard error estimate to stop, we get already improvement, but then also averaging iterations helps us much more, and still increasing number of dimensions makes it more difficult, but we get much, much better performance. So now these R hat and Monte Carlo standard error there were only for the convergence of these variational parameters, how close they get to the optimum, but they are not yet telling how good that actual variational approximative distribution is. And the resulting approximation can be bad. For example, we are often using normal distribution, and if the target is not close to normal and it's high dimensional, it cannot be good. We have a paper discussing how we can assess the goodness using importance sampling diagnostics, and then that's why I included these importance sampling diagnostics also in this talk. In addition to diagnosing and improving variational inference and other distributional approximations like Laplace approximation, we can use it also like we commonly use it in importance sampling leave-one-out cross-validation, and we are using it also for prior sensitivity diagnostics. So in importance sampling, we have some interesting target distribution which can be unnormalized, and in this case then denoted by Q, and so here in the plot, and we have some approximate proposal which could come then from this variational inference, shown then with the red dash line. Now it's easy, for example, if this is normal distribution, this proposal, to draw from the normal distribution draws. And then we can use these draws at every draw, we know also that we can evaluate this proposal density and unnormalized target density, and then we can compute expectations using weights. So weighted expectation, where these weights are just ratio of the unnormalized target and this approximate proposal density. And here you can see this would be then the importance function. So we need to weight more draws from here and weight more draws from here and weight less here. Now the variation of these weights affect the effective sample size. If single weight dominates, we have effectively just one draw. And if the weights are equal, then we have effectively S draws. If weights are equal, then actually our proposal is the same as the target. Central limit theorem holds only if variance of the weight distribution is finite. So we would like to know also that. And then we have a paper discussing diagnostics for this. Pareto K diagnostic, I mentioned this Pareto distribution before. So we can look at these largest weights, the tail of the weight distribution, and fit their generalized Pareto distribution and look at this tail shape parameter and infer from there so that if the k is less than half, the variance is finite. We are going to get very good estimates. And even if the variance is infinite, generalized central limit theorem holds. And then we can show in practice and justified also with theory that if the k is less than 0.7, error rates are reasonable. We get small errors with high probability when the number of draws increases. Okay, illustration of then how this importance sampling diagnostic and correction works. This is just a two-dimensional example from this is a bioassay example from Bayesian data analysis book, used also in my course. So the true posterior evaluated in fine grid, draws from there. And in this case, we are also interested in this lethal dose 50, which happens then to be minus alpha divided by beta. So here we have alpha and beta there. Normal approximation, which is now just normal approximation at the mode, but we could use also variational inference. It looks a bit of similar. It seems there's a bit more mass for small values and less mass for larger values. We can get draws and we can use these draws to compute LD50. Now this distribution seems a bit wider than this one, especially draws from the far tails. And if we compute standard deviation of LD50 from the accurate estimate, we get 0.1. And now the normal approximation is giving us estimate which is 7 times larger. So that's not good. But we can use importance sampling to correct that. We could compute these weight and expectations with weighted draws directly. But in this case, I've used resampling, importance resampling using these weights. So some of these samples are then presented more than once, and then some of the draws are not presented at all, and then kind of how many times these resampled draws are there correspond to these importance weights then. And now this looks more narrow, and we can also check that yes, we were able to get good estimate for this LD50. Let's zoom a little bit on this result here. So these were now the draws from the accurate sampling, and then these are draws first from the normal distribution and then resampling. And you can see there's these bit of clusters, it's because I did add some jitter to show more clearly that some of the draws have been resampled several times. So these clusters are actually exactly the same values, just repeated many times. So this seems maybe a bit of problem that have these kind of clustering, kind of reducing the accuracy of this. And this is something that we can analyze now by looking at the distribution of the weights. So these are now the distribution of these weights, and we can see here there are some big weights. So these are quite low bars, but I can help you to see them. And then more and more here. It's good that this, even the largest, is not having a weight 1, so not completely dominating. And if we look at what would be the weight values if they would have equal weights, there are a lot of weights around here, so not that bad, just few larger values. Instead of just looking at these kind of plots, we can also compute then effective sample size using this rule. This is based on variance of normalized weights. So normalized, this tilde is a normalized weight, which is just self-normalized, the weights divided by sum of the weights. And for example, in this case, we get an effective sample size 270, not that bad. But we can also look at, is it possible then that actually this variance estimate is not that good because it might be infinite? And now we would like that Pareto K diagnostic, so the kind of the how thick this tail is estimated by fitting generalized Pareto distribution to the largest weights. It would be, we hope that this K would be less than 0.7. Oh, it seems that we are on the Porter case, and it would be useful in this case run the draw more of these draws and then get more accurate estimates for the K hat and also then more accurate estimate for the effective sample size. But it's still possible that we are actually kind of in the good range. This is one important thing is also that now actually these tilde W weights, what we are using are not the raw normalized weights, but we are using also Pareto smoothing, which improves the behavior. And so this Pareto smoothed impedance sampling has finite variance of the estimate. And then this is just related to what is the practical convergence rate for our estimates. So this Pareto K, so the K estimates the number of existing moments, and then we have a finite variance in central limit theorem holding if K is less than half. Finite mean and generalized limit theorem for K is less than 1, but then we have both extensive experiments and theory showing that this pre-asymptotic constant grows impractically large when K is larger than 0.7. Of course, so this is not sharp threshold. And when we are estimating the K hat also, there's uncertainty in that. And so if you're close here, just draw a bit more and check if you can get K below 0.7 and if the ESS keeps increasing. We can get for the impedance sampling also Monte Carlo standard error. Again, the variance of theta divided by effective sample size, square root, and also in impedance sampling case, we may have different ESS when estimating expectation of theta or expectation of some function of theta, and see these function-specific ESS formulas in our paper. And here's then how this iterate averaging, that in addition of that we get then these variational parameters closer to the optimum, how it affects the actual approximation to the posterior. When the number of dimensions increase, the increased variation, kind of the stochasticity, if we use just the last iterate, make the approximation quickly really bad, and shown also by then this Pareto smoothed impedance sampling k-hat. But if we do iterate averaging, we get closer to optimum, and then these approximations are also better behaving. So for the variational inference, I did discuss R-hat and Monte Carlo standard error for analyzing the optimization phase, and then effective sample size and Monte Carlo standard error based on impedance sampling corrections and diagnostics, and Pareto K for looking also then the convergence rates. As a bonus, what if we have a multimodal case and the modes are such that like Markov chains are not mixing between them, or the variational inference optimizations ends up in different modes? We can run many chains, many VI optimizations, but there can be cases that there are so many modes that we don't even know when we have found them all. So how do we then analyze convergence? If we can assess the convergence locally, that in each mode we think that, okay, Markov chain is working well, or VI has converged in that local mode and is presenting that local mode well, then the question is just that how do we analyze this multimodally? And then we can use stacking, which is then an approach computing model averaging weights, but in this case we can use it also for chain averaging or VI averaging, so that these weights are optimized to give good predictions. And then we can see that if we are running more chains or VI runs, when the stacking predictions don't improve anymore, then we've kind of found enough many modes. And then we can kind of examine the convergence of these stacking predictions. Okay, finishing here. So these are a few of my favorite inference diagnostics. So run inference many times, and then different convergence accuracy diagnostics for MCMC, VI, impedance sampling, and stacking for non-mixing cases. And most of these are already implemented in packages like RVs, posterior, blue, baseplot, RSTAN, ARM, command stan, and some others. Here are the references, and thanks for all my co-authors. And you can find all these and links to references on my publication webpage. And then also thanks for all people been implementing these different software. And so here are also the software references.